All right. So my name is Chris Pope, software engineer in Rochester, working on the Digi platform. My presentation is going to be on dynamic analysis of concurrency on the JVM. So most of this has been a course project for my advanced topics in software engineering course that I'm taking at the University of Illinois. And so the intent of this project was to have a plugin framework that would do dynamic analysis to detect concurrency issues in your programs. Kind of the overall goal is to more help improve program correctness. A lot of times programmers don't necessarily think about concurrency and threading and all of that when they're coding. They may write something that they think is going to be executed serially, and then later on 10 threads come in and mess it all up. So really what the goal is to kind of provide them hints. It's like, hey, you might want to take a little more look at this code, not necessarily say there's absolutely a problem here. So eliminating false positives on that aren't necessarily a goal. So it's going to utilize a plugin approach. So it's kind of just an architecture overall, and then you have individual detectors that implement different things. And one goal was to do all of the concurrency analysis in a single run of the application. A lot of the stuff I had read about, it actually had more than one phase. Like you might have like a learning phase, like training, and then it would actually generate a set of rules that would then be applied to subsequent runs. I wanted to avoid that. Particularly for like some of our products, they're more long-running. So you'd actually start them up, manually stress it or use it or whatever, and then that seemed to fit a lot better than some of the other approaches. So I'm going to talk about kind of what my solution looks like overall, how it works, how I did some of the bytecode instrumentation, some of the different papers I based the detectors I wrote on, and then just some links of other relevant research that's useful if you're interested in this area. So here's just some sample code that I ran it on. Really all this code does is, on the left, it just has two lock objects and two threads. And then all it basically does is have each of the threads run and then do the code on the right, which basically has them acquire the locks in reverse order and then seek for 500 milliseconds. So it's just something that will stress the code and potentially cause a deadlock. And then to run what I wrote, you just basically specify some virtual machine arguments that specify your agent that will instrument all of your code. And then you also have to specify the packages that you actually want to have instrumented as well. So, let's say you have a bunch of third-party libraries. You don't have to include those as packages that will be instrumented if you know they're just going to be, including a bunch of noise. The way it is currently, I have a main method you have to execute, and then that main will actually have to call into whatever you're actually running and start it. That's just kind of a temporary thing. Ideally, it would all just be, contained in these virtual machine arguments, and you would just, execute your program however you would normally.
The agent is your analyzer?
So what the agent actually is it's actually what's going through and doing all the instrumentation. So it's the thing that's doing all the instrumentation of the classes, so it has the class rewriters and all of that. Yep. So there's kind of two parts. There's the agent that does the instrumentation, and then the main method of my thing is actually the thing that loads up all the plugins and registers them as listeners in the instrumented bytecode. Yep. So here's the XML file that I have. You basically specify the class of the different detectors that you have, and then whether it's enabled or not. So once somebody's actually using this framework, if they were to implement their own detector, all they have to do is make sure it's on the class path, and then they add it to this XML file, and then it'll actually just load it up and call their detector back with all the necessary information. And then so here I have, as you can see here, I just have the reversed order lock detector as enabled, and I'm going to run it on the code that I had at the first slide. So the output really needs to be cleaned up a little bit, but you can see I'm loading detectors, and I'm starting that little test code, and then that detector is actually reporting that it found, hey, with these two locks, they were basically, one thread was trying to acquire, and then in a previous situation, the other thread had them in a different order in its lock graph. So, and it just finishes the test. So that's a kind of a trivial implementation of a detector. So then, how it works? So it uses a library called ASM to instrument the bytecode on startup, and that's what the agent's doing. It has the plugin loader, the main that actually reads in the XML file, and then it uses reflection to load up the detectors. And the detectors are added as listeners to that one agent. And then the detectors, in the framework, I have a report method that they can call and basically report their findings to. So in this slide, that bottom there, the reverse lock order detector actually called the report method and gave it this. So then you could do things like, have it print out in like the JUnit format or whatever format you want to for your results. That's just, right now it's just kind of a console output. And then, let's see. So
these are runtime detectors?
It's all runtime, yep. No static analysis, it's all dynamic, yeah. Yep. So then here's just the listener that each detector has to implement. They can call the report method, which as you can see right now just prints it out. And then they have to, have a name for their plugin. And right now there's before forking, which basically says, hey, a thread's about to be spawned. Or there's just before event and after event. And then for the before and after event, they have the different events at the bottom that they'll be notified on, like when a field is accessed, if a lock is unlocked or locked, if a thread is doing a join, if there's waits, it notifies, threads are being spawned or dying. And then like the field access event, it basically tells you which class is the field in, what's the field name, and then it'll give you the particular hash code of the object that is being accessed. So for the bytecode instrumentation, I actually based it off of another project at UIUC called REX. REX, their goal was to actually instrument the bytecode, and they actually intercept all things like synchronization primitives. And what they actually do is they actually don't allow the JVM to execute those. They do it all in code manually. And the reason they do that is they actually totally control all thread scheduling. So their goal is to basically have some unit tests you run, and then it's re-executed with all the different possible thread schedules that are interesting to find the different potential concurrency issues. So you have like a unit test that stresses it for concurrency, and then you'll actually find all the potential failures with all the different thread schedules. And they do all the sort of things like pruning, impossible schedules and all that sort of thing. For my purposes, this was way overkill. I actually wanted the JVM to do things like the synchronization and handle all of that. So what I did is I stripped out a lot of their code and just took out the listener stuff so that I could actually be called back on events and all that. I added some additional extra instrumentation with ASM to do things like for the field event, they only gave like the class name and the field name. I added things like the instance, the actual hash code of the object.
How does the re-ex handle mutable code where it's actually changing things? How do they re-execute it over and over again?
Well, so you have a unit test, and then it's just you execute the unit test multiple times. That's how it works. Yeah.
So each invocation is fresh.
Exactly. So it's not applicable at all to a long-running application, really. Okay. Yep. So what was really useful and interesting is actually the ASM tools. So I have a few slides here to talk about that, how you do the instrumentation, and what helps a lot. So here's a plugin for it. It's what it actually shows you is on the right there's the Java code, so it's compiled down to a class file. What they actually show you on the left is here's the bytecode representation decoded of that class file. So you can see all the different things, what is it. So it helps you kind of figure out, what does the bytecode actually look like that you're going to be modifying. Because it's actually not straightforward to actually do the transformation. And the way that ASM actually works is it takes an input class, and then it has a bunch of transformers that you apply, to do things like, add methods, add fields, and all of that. So in this next view, now instead of showing the actual bytecode, they show here's what the ASM representation of a transformer would look like to create that class file. So now you can do things like, make a change in the right there and see here's the code I would have to have in my transformer to actually make it have that new method or whatever. And then what's kind of nice is they actually have a diff view as well. So here's two classes, and then I'm showing the diff at the bytecode level. And then once again, here's the diff of the transformers. So you could have your original one, and then it'd be like, well, I'd like it to, call this method in this listener. So you actually put it in your source file, and then you do the diff here of the transformer, and then pull that out, and then now you know what your transformer looks like to modify it so it actually calls back. So without that, it was really hard because you actually have to go in and read a lot of the, like how does bytecode work and all that. With this, it's more like, well, you kind of have to have an idea, but you can just kind of use their stuff. So these tools were really nice, and it makes the instrumentation and transformation of bytecode a lot easier. So as you can see, it's actually very easy to take a class file and modify it to add additional methods and everything. So don't think your class files are secure, so here I'm going to talk about some of the detectors I wrote. So the one I show, that I researched how to write. So the first one I showed is the simple potential deadlock detection. It's just really basic. It detects potential deadlocks between two threads and two objects. If a deadlock requires 3 threads or 3 objects, that sort of thing, those will pass by without being detected. So the research that I followed on with was how to write a better potential deadlock detection plugin, and then 2 different frameworks for doing data race and atomicity detectors. So this one, Here's a paper that I kind of got most of this from. What they actually do is, let's see. So theirs is actually based on 2 stages. They have the first phase where what they do is they basically log out every single lock and unlock event that happens in a file, and then they go through that graph and they look for all the possible cycles, and then they basically kind of save that out, and then in the second run, they actually control the thread scheduling to push all of the scheduling to those deadlocks. So they did that to reduce a lot of the false positives. So like the first case, like here's a bunch of potential deadlocks, but hey, maybe a lot of them will never actually happen due to the way that threads are scheduled and all that. So they ruled out all the false positives by the second run is what actually tells you results. Hey, a deadlock occurred. I forced it. So they based their actual algorithm for doing the recording of locks and the checking for cycles on another paper. What they added was some concepts about reducing false positives at that level by removing threads that are only regarding a single thread, because you can have reentrant locks. That's totally fine. Cycles and/or gate lock. Maybe in the 2 thread graphs, they both held like a common lock before they actually had the reversed order, so that could never deadlock. And then, just thread segments that would never actually execute in parallel just because they're totally different, parts of the life cycle of the application. What they covered in this paper, similar to mine, a lot of the deadlock detectors out there didn't actually handle a lot of situations where there are more than 2 threads or more than 2 locks. So what I had kind of explored a little bit is how do you actually combine the detection, like the graphs and the unlocking, all that, and the actual checking for deadlocks into a single case. So what I would actually do is probably take just the first half of it and allow more of the false positives to kind of flow out and be like, hey, these 2 threads might actually be deadlocking. Here are the thread names. Here are the objects involved. Do you think this could actually happen? And then the user gets to decide. So Cord, this one is for data race detection. So the paper kind of focuses a little bit more on hardware-oriented stuff. Let's see. But some of the stuff was very interesting, even if you could implement in software. Basically what they did is each memory access, they timestamped it. It was not a typical timestamp. It was just kind of like a sequence number more so that incremented whatever thread did a memory access. And then the mode of the reader-write. So then they did it a hardware thing, so they did things like only keeping 2 timestamps for the memories that were actually in cache at the time. So the paper goes into a lot of details on that. And then when an access occurs, they'll compare like the thread's current logical time, and then if it's actually before the logical time of the memory access, then they know that it was actually another thread that updated it, and then the current thread will say, oh, this is a potential deadlock or a data race, and then update its clock to be the same as that one. And then the paper goes into a lot more detail, but it's pretty interesting. One of the things that they point out is with their very simple hardware modifications, there would be very little overhead when you actually execute this. So you can actually train it, produce, the sort of, and then you could run it in production or whatever, and they would actually just find them all. And it actually kept history so you could recreate it and all that. It was a rather interesting paper. So then Avio. So this one is for atomicity violation detection. So you see in the code in the upper right-hand corner, there's a couple of one variable involved. So what they actually do is they lock, and then they set the current script to something, and then later on, and if they're expecting to execute serializably, yeah, there you go. They'll actually they lock again, and then they actually call a method on that object. And hey, I did locking all that stuff. It should be good. But then what happens is another thread actually goes in and sets that current script under the lock to null. So then even though you don't have data races or anything anymore, you're still going to get a null pointer exception because you have an atomicity violation. The programmer expected this to act this way, but it didn't. So what Avio actually does is it goes through the code, and it looks for things called access, interleaving, and variance. What it does is it basically looks at each pair of memory accesses and sees in a typical run of this application, are these always accessed serializable? In a serial manner, yes. Choose some different words there. And then if through a couple of training runs, it actually determines that the 2 accesses are always accessed in a serial manner, it'll kind of put that out as an invariant. This is always true. And then in a subsequent run, it will actually kind of turn on all of these invariants and check to see are all the accesses complying with the invariants that I've created. So it was an interesting paper as well. In the paper, they describe both hardware and software implementations. Once again, since my goal is to condense all training and checking into a single run, what I would have to do is kind of generate my invariant and have some sort of algorithm that's like, if there's 10 subsequent accesses in this manner and they're all serial, then kind of consider the invariant activated and then start using it to check. So that's kind of how I thought I might make use of that in the detector in this. So then, yeah, here's some other papers that you can download from my presentation on Google Docs and just read more about different concepts in concurrency on the JVM. And cool, 2:15. So there we go.
Okay, I got a question. Are there like
sure.
Are there like any like tools out there that are like just kind of popular tools that you can use? Kind of like you mentioned, kind of the challenge of having having something running and then having some kind of deadlock detection going on in the background that kind of catches that. Is there anything like that out there, or it sounds like it's very challenging?
Like what I found is like through all the research I read, a lot of it's just kind of like we don't really care how this works in production. We just want to kind of test our theories. So a lot of it does break it into kind of the training and then the checking phase. They don't really kind of do it all at once. And they have some kind of like, here's what the results look like, when we try it against Mina or this or that sort of thing. But they're not really production ready. Okay. There were some applications that kind of implemented like very old ideas, but they would only do very simple things like hey, there's a deadlock that actually occurred, right? Not like more useful information.
Like what was like your kid is really just looking for actual deadlocks. Is that true?
Yeah, I don't think it does too much for like the data races and all that stuff at all. So what I kind of wanted to kind of explore with this was like with find bugs, a lot of people can actually write their own detectors for find bugs. So if and then you can kind of pool together your resources and all that. So with this, you provide a very easy way for them to write listeners, and then they can, read research or whatever they want to do and implement their own detectors, and they can actually share them. And you can just download them, put them in your class path, and enable them in your XML file. And then kind of with the focus on concurrency, then you might be able to read, write much more specific ones that could actually find things, but they're not, some global, very interesting research, I guess.
Yeah, I think the point you made of we're writing things that we expect to be executed serially, and we don't realize everything else is going on at the same time. It'd be kind of cool to be, hey, I introduced this code into the platform. Is there any negative impact to a running environment, running some kind of scenario?
Yeah, because it would be interesting to actually add to here, like the ability to say, hey, I've already seen this one before. Don't print it out again. Then you actually have the same thing with find bugs. Like maybe you could run this on a subsequent release and then see are there any new things from the previous one, and then you can investigate those quick and then just check them off as, yeah, it's totally fine, or maybe there was a problem.
Problem gets a lot worse when you start using things like terracotta.
Yeah, that's one thing that actually.
Terracotta lock.
Yeah, what I thought was kind of interesting because like terracotta is a very similar thing where it actually instruments and just like the React framework actually didn't allow the JVM to handle the locking. It actually did it itself in code. I mean, that's exactly what terracotta is doing. It's not having the JVM lock it. It's actually handing the lock over the network and say, hey, can I synchronize on this? So that's one thing I didn't have a chance to play around too much, but I wanted to try running this with our stuff and see how does the instrumentation I did play with theirs, and could I make it actually work well.
You haven't tried that?
I have not, no. Yeah, I figured it probably wouldn't. So then it wouldn't be all that useful. So, any other questions at all?
On the course paper,
yes.
Why was there a learning phase? It's doing hardware counting.
Yeah, so actually in this one, I might have spoke there. I don't think there is actually any sort of learning phase there.
Okay, yeah. Cause it's,
Yep. So that one actually is able to just do it all. It just looks at the data accesses and the data races and everything. Yep, that's correct. It's only the deadlock one and the alveo that actually has learning phase.
And have you considered doing markup for alveo?
So what do you mean markup?
You can do markup instead of learning phase to say, I assume this is going to be atomic.
Oh, yeah, that's true.
I mean, but then you can't use your current code.
Yeah, because and a lot of the thing is programmers don't know when they have problems. So I don't know. If you knew that your code was going to be accessed by a bunch of threads and you were really thinking about that and you marked it all up, then it's probably much less likely to actually have problemes than the arbitrary code that's not marked up.
So from making developers think anyway.
I guess yes.